For as long as humans have looked up, the moon has refused to be just one thing. To some, it was a god, to others, a calendar. To sailors, it was a guide, to farmers, it was a clock. To astronomers, it was a world, and to NASA, just before Apollo, it became something even stranger, a place close enough to reach, but still full of things no one could quite explain. Strange lights had been reported on its surface. Spacecraft refused to orbit it exactly as predicted. The moon looked dead, but it didn't behave like a dead world should. By the 1960s, the moon had been mapped, photographed and studied more than ever before. But it was still not a place that humans had visited yet, and that meant that NASA had to answer a question which sounds quite simple, but it isn't. Was the moon truly dead? Was its surface stable? Was its gravity predictable? Were reports of flashes and glowing patches just mistakes or signs of something still active below the surface? If astronauts were going to land there, orbit above it, take off again and rendezvous in lunar orbit, then probably was not good enough. NASA needed to know answers. And that problem has not really gone away. Even today, when we talk about going back to the moon, the issue is not just finding information, it's working out how that information is being framed. A good current example is NASA's Artemis 3 crew announcement. On Ground News, this one story has hundreds of articles from sources across the political spectrum. Another headline says NASA has revealed the Artemis 3 crew for one of the most complex space missions ever. Another frames it much more cautiously as a 2027 Earth orbit test flight. Both are talking about the same mission, but they lead you to think about it differently. One makes it sound like a dramatic next step back to the moon, whilst the other reminds you that Artemis 3 is now a test mission in Earth orbit designed to prove docking and life support systems before the later lunar landing attempt. That's why Ground News is useful. It's not a publisher, it's a layer of context on top of the news. It lets you see how many outlets are covering a story, compare headlines side by side, and check source bias, reliability and ownership at the publication level. It's also a good fit for this channel because Ground News was founded by a former NASA engineer, and the whole idea is to look at the bigger picture rather than just one version of events. And now you can get 40% off the Vantage plan for unlimited access by scanning the QR code on the screen now, or by going to ground.news/droid. The link is in the description below. For centuries, people had reported temporary changes on the moon. They described bright flashes, hazy patches, reddish colorations, and strange glows that appeared, changed, and disappeared. Some reports were almost certainly mistakes. The moon is a difficult object to observe. Its surface is full of harsh contrast. Turbulence in the Earth's atmosphere causes the image to shimmer. The angle of the sunlight changes dramatically from night to night, and human colour perception through early telescopes was not always reliable because of chromatic aberration. But some reports were harder to dismiss. Again and again, observers pointed to the same regions. Aristarchus, one of the brightest craters on the moon, Schroeter's Valley, a winding channel nearby, and Alphonsus, a crater which had already attracted attention because some believed it might show signs of activity. If the moon was completely dead, then why did these places seem to repeatedly catch people's attention? In the mid-1960s, with Apollo approaching, NASA backed a project to look for these events more systematically. It was called Project Moonblink, and it would be done with a network of 12 professional and 4 amateur observatories. If part of the moon temporarily changed colour, especially if it became redder or bluer than the surrounding surface, then a normal telescope observer might miss this. Moonblink used a rotating colour filter wheel split between red and blue filters. If the lunar surface was normal, then the image would remain steady. But if a patch became unusually red, it would appear bright through the red filter and dark through the blue filter. To an observer looking at a section of the lunar surface, a light anomaly would show as a blinking area in that part of the moon as the filter wheel rotated. If one station saw something, others could be alerted to confirm they had seen the same thing. This was in effect a lunar surveillance network before modern automated astronomy existed. But while some scientists were looking at strange lights on the moon, another team was finding something stranger still, and that was that the moon's gravity was not behaving as it should. Before astronauts could land on the moon, NASA had to map it. The Lunar Orbiter spacecraft were sent ahead to photograph potential Apollo landing sites. But their cameras were not the only instruments being used. Every spacecraft in lunar orbit sent back radio signals to Earth, and by measuring the tiny Doppler shifts in those signals, engineers could tell how the spacecraft was moving. This is where NASA found something unusual and potentially serious for orbiting spacecraft. If the moon's gravity had been even, the orbits should have been predictable. Not perfectly super smooth, but close enough. A spacecraft should have followed a clean, mathematically predictable path around the moon. But the tracking data they revealed said otherwise. The orbiters were being tugged, accelerated and slowed in ways that didn't match an even gravity field. At first, this was just an orbital problem, a mismatch in the numbers. But when scientists looked closer, the pattern began to reveal something hidden beneath the surface. The moon had mass cons. This term stands for mass concentration. These were regions where the moon's gravitational pull was stronger than expected. They were not mountains or visible cliff edges. A camera could not show them on a photograph. They were invisible lumps in the moon's gravitational field. Many of the largest ones sat beneath the Great Lunar Barrier, the dark seas visible from Earth, such as Imbribium, Serenitatis, Crisium, Humorum, and Nectaris. To the eye, these looked like smooth dark plains, but to a spacecraft they were gravity traps. For the MASCON researchers, the question was more fundamental. Why was the moon's mass distributed so unevenly? And what did that mean for spacecraft flying just above it? These were not just fringe concerns, they mattered directly to Apollo. Those brief moon flashes of colour might reveal outgassing from the lunar interior that would mean the moon was not completely inert. It might have pockets of trapped gas, fractures, or regions where material could escape. If the flashes were impacts, that mattered too. The moon has almost no atmosphere. Meteoroids that burn up harmlessly on Earth could hit the lunar surface directly and intact and cause severe damage to a lunar lander, or possibly an astronaut. Understanding the rate of impacts matters for spacecraft, surface equipment, astronauts, and future bases was vitally important. However, for Project Moonblink, it was turning out to be harder than expected. The light flashes were transient and random, and having human observers sitting around and waiting for a random event to occur meant that the network was difficult to sustain. Volunteers lost interest, equipment was limited, the hoped-for automatic detection system was harder to build than planned. This left NASA with a frustrating answer. Yes, some things were probably happening, but the evidence was not clean enough to say exactly what they all were. MASCONs were different. They were not fleeting. They did not depend upon a lucky observer at a telescope. They showed up in tracking data again and again. The Apollo missions were not simply a matter of flying over the moon and dropping straight down. The spacecraft had to enter lunar orbit. The lunar module had to detach, descend to the surface, land, and then the ascent module had to take off again and meet the command module still orbiting above. That rendezvous depended upon knowing where the command module was. If the moon's gravity field was wrong in the models, the orbital predictions would also drift and be wrong. Maybe by not a catastrophic amount in a single orbit, but enough that engineers had to understand it, correct for it, and build it into mission planning. However, the lower the orbit, the more important the local gravity became. A MASCON could tug a spacecraft forwards, backwards, sideways, or downwards, depending upon the craft's path. Over time, these tiny pulls could reshape an orbit. Around the Earth, low satellites are dragged down by the atmosphere. Around the Moon, a low satellite can be pulled into trouble by gravity itself. The lunar orbiter tracking improved the gravity model. Apollo 8 tracking added more. Later missions refined it further still. This mattered because every move to correct an orbit required fuel, and there was only a limited capacity for this fuel. Engineers learned that low lunar orbits were not automatically stable. Mission planners had to account for gravitational anomalies, carry fuel for correction burns, and choose orbits carefully. Some lunar orbits were more naturally stable than others. These were sometimes known as frozen orbits, where the gravitational perturbations balanced out well enough so that a spacecraft can survive for much longer without constant correction. The Apollo 16 sub-satellite, PFS-2, was a small 80-pound scientific probe deployed into lunar orbit on the 24th of April 1972. Its primary mission was to map the Moon's gravity field and study its plasma, particle, and electromagnetic environment. But it showed what could happen when an orbit was less than favourable. Due to problems with the main engine, the probe was released at a lower than expected orbit, and where it was subject to the mass-con pole more than it would have been if it had been in its original orbit. Its mission was meant to last about a year, but its low orbit was rapidly altered by the gravitational perturbations, and it crashed into the Moon after just over a month. The mass-cons were eventually understood as relics of giant ancient impacts. Billions of years ago, large asteroids and comets slammed into the young Moon. These impacts excavated huge basins, disturbed the crust, and in some cases allowed dense material to rise or melted material to pool. Later, basaltic lava filled many of these basins, creating the dark maria visible from Earth. The result was not just a visual scar, but a gravitational one too. Where the Moon looked like a flat, dark sea, the mass below it could be denser than the surrounding crust, and this region had a stronger pull on spacecraft passing nearby. Modern missions, especially NASA's Grail, flew twin spacecraft Ebb and Flow in tandem around the Moon to map the variations of a lunar gravitational field. The probes generated the highest resolution gravity map of any celestial body to date, and at the end of the mission, the probes were purposely crashed into the Moon. For Moonblink, the lesson was more complicated. Some strange lunar flashes were known to be real impacts. Modern lunar impact monitoring uses telescopes and video cameras to watch the dark part of the Moon for brief flashes when meteoroids hit the surface. This doesn't explain every historical report. Some reported events lasted too long to be simple impact flashes. Some may have been due to outgassing, dust, observation effects, atmospheric distortion, or just simple observational mistakes. The modern view is that not all the old observers were wrong, nor that every strange report was a mystery beyond science. The truth is that the Moon is mostly quiet, but not perfectly still. It is hit by space debris, it has moonquakes, it cools and shrinks. The surface dust responds to extreme conditions. Its weak exosphere and possible outgassing events are still scientifically interesting. And with our latest Artemis missions and the long-term plan for bases, we will need to know what the Moon is and what it does, as well as we know the Earth here. You can't just run outside in case of an unexpected event once you're on the Moon. So I hope you enjoyed the video, and if you did, then please thumbs up, share and subscribe. And a big thank you goes to all our patrons for their ongoing support.